Thank you. And my apologies, I'm unfortunately running this on a different laptop than it was for, so some of the fonts are a little bit off, but I'll do my best to describe the slides so that if there are any confusions, it's still easy to see what's going on them. So I'm going to be talking about non-visual interaction techniques at the keyboard surface. And we were inspired in this work by the sort of, I think, a common understanding that web access and access to online materials is really a critical thing in today's society. It affects our ability to participate in education, jobs, and so on and so forth. And as a result, we've seen a lot of effort go into improving web usability, but this has at times left behind people who are blind. And in particular, there are aspects of web usability that are harder to deal with, such as these kinds of tabular layouts that can be more difficult to process using a screen reader. There are sometimes issues with understanding the relationships between different items on the screen in space, and or with being able to navigate through them in a sensible order. So the screen reader can be really efficient for expert users, but as we will see in the user study results, for these kinds of interactions, it can be harder, even with a screen reader, to access the web than we'd like. And there are some really great studies out there that articulate these problems. So Jonathan Lazar's study with 100 blind users points out that understanding page layout is hard, for example. Similarly, there are other works that articulate the challenges of accessing non-linear web widgets, such as menus. And this is where we focused our efforts in this project. So let me go on. There's two approaches to dealing with these kinds of problems. One is mapping GUIs to auditory interfaces. And some of the original work in this area, for example, Beth Meinet's was, I think, even inspirational in terms of how screen readers work today. And a second thing is using specialized aids to improve the accessibility of the web. So in the case of auditory interfaces, we can do things like convert aspects of GUIs like icons into audio, not only speech, but potentially also non-speech audio that helps to reflect on what's going on. But they are, for the most part, limited to linearity because audio is an ephemeral medium that comes out in order, right? And maybe a little bit of overloading. So there's a lack of sort of spatial awareness that can be conveyed easily in audio. In contrast, we can think about work that a large segment of the blind population do understand Braille, not everybody, and so we can think about Braille as something that potentially can convey more than one dimension of information. So that's an alternative approach, but still, most Braille displays today are linear, and so there's still a limit to how much spatial information can be conveyed. And then recently, there's been work looking at overlaying things on touchscreen displays in particular that can provide a more spatial set of cues. And so we can make, for example, large touchscreens accessible by using fabricated templates on top. And this is work that Sean Kane was involved in, for example. And this can then support new kinds of interaction techniques that go beyond just using keyboard input. And so we can start to allow for a better understanding of spatial information, or even support interaction that sort of places search results, for example, in a spatial layout that relates to where they are on the page. So there's some really positive things that can come from adding tangibility to how we deal with this, even static tangible displays. But it's hard to generalize this to a wide range of applications because these are static templates as they were originally designed. So there's no easy existing technique right now that is like really flexible and able to allow exploration of two-dimensional information that is readily usable in blind interaction. And so we developed SPRITEs, the Spatial Regional Interaction Technique. And the key insight in SPRITEs is that the keyboard, although it is not normally thought of as a spatial input device, in fact is a pixelated two-dimensional surface. Not only is it two-dimensional and pixelated, but it is eminently deployable because it is available with every computer. And so it could be used for two-dimensional interaction or interaction that has spatial components, for example, hierarchical mappings. And the key distinction on the keyboard is the keys, right? There's 90 of them on the keyboard surface. And if we think of these as pixels, it's a lot higher fidelity than many other options that are available for spatial interaction. So it provides us an opportunity to think about a 2D interface. And I want to emphasize here that this is not a novel text input method. This is really rethinking the keyboard as a two-dimensional input device. In addition, it's a really familiar technology. It's one that has markers on it that help you orient your hand. There's a lot of positives to using the keyboard. So it is an economical and potentially valuable way to deal with 2D input. And now I want to show a video demonstrating how we make use of the keyboard. So this is a web page, a Wikipedia page, and what you're seeing in highlighted is the current focus of the keyboard interaction. And let me just make sure I have audio, forgive me.
Text block.
Can you hear that?
Text block.
So I'll just explain since there's no good audio. This is now mapped into a scroll bar essentially. Okay, so the interaction technique here is that you can cycle through things on the web page, and if you get to the bottom one here, if you run out of space, you press that key and it will then flip down to the next set of text blocks and map them onto those green keys. So you can essentially work your way through the contents of the page by scrolling through things.
Further, the keyboard size depends on the extent to which a system is used, where a single action is produced by a combination of subsequent or simultaneous keystrokes.
So what the user's doing is they're moving their hand from key to key. They're pressing on each of these things. If they press twice, it reads out the contents of the text block associated with that key. If they press once, it just says what the type is. Is it a text block? Is it a header? And so on. And so this is a way of sort of navigating through these kinds of items on the web page. We can also do menus and lists. So in our implementation, after some pilot studies, we realized that the edges of the keyboard were really important homing spaces for the hand. And so what we do is we tend to use the regions along the edges of the keyboard as the primary interaction regions for much of what we're doing, because it's easier for participants or for people who are using this to find those spots. And as you saw in the video, any kind of group item could be mapped onto region 3, but we actually find for menus or other things where we have a larger number of items that when possible it's better to map it onto region 1 because it's got a larger number of keys in it. And so this horizontal region is really valuable for that. It's also really valuable because there's a natural succession of regions when there is a hierarchy. So for a menu, we can map the menu bar essentially onto region 1. If somebody selects a menu, rather than replacing what's on region 1, we map the submenu onto region 2. So the menu bar would be across the top of region 1, and then if you selected, say, the file menu, you'd have open, close, and so on mapped onto the keys where it says nested, which is this sort of nested region 1 area. And if there was a submenu within that, that would just map onto the next row. And this allows for a kind of interaction where somebody can have a little bit of memory of what was there. They can go back and forth between things. They can even use sort of a proprioceptive approach to sort of going, okay, this is familiar, let me come back here. And so that's how we deal with menus and sprites. We also reserve region 3 for browsing, so that even when the menus are mapped onto region 1, it's still possible to go up and down in the focus on the page using region 3. So this allows for some parallelism. Okay, so let me show. So this is, again, horizontal movement through grouped items, like menus and lists. This is really what we reserve for scrolling. And here, this is vertical movement for 2D widgets such as tables, and I'll show that in a minute. So we also support that. What we're doing is taking some of the techniques that were shown to be successful in other kinds of tangible interaction, like the overlays, and mapping them into interaction techniques on the keyboard. So for example, 2D projection is a way of taking things that are in a table and sort of projecting them onto the edges of the keyboard, or onto the edges in overlays. And here we're projecting them onto the edges of the keyboards. If somebody wants to search, we can actually project the search results onto the edges of the table rather than having them have to seek through the whole table to find things. So let me show examples of this. So here is an example of a table that's been mapped onto the keyboard. You can see the key highlighted that corresponds to the table cell. So the upper left table cell is selected here, and then the upper left key on the in region 1 of the keyboard is also selected. And so if the user presses the key twice, it reads out the contents of that table cell, which is employee ID, but if they press it once, it reads out the location, row 1, column 1. So this helps with orienteering or orientation. And we always start from the top left selection for each dimension and track it independently. So if you move across the top row of the table, we will change which column is selected of the keyboard. If you move down the left column of the keyboard, we change which row is selected, but the column selection remains. So here we're moving over to the next column, first name, and that's accomplished by pressing the number 2 on the number row of the keyboard, which is region 1. And if they press the next row of the keyboard in vertical, then they also get the next row of the table. So there are two things to note here. Again, it moves you vertically down in the table, but it retains the column selection. So we're now in column 2 and row 2. Okay. So we also support searching in tables, and here we have the same kind of horizontal and vertical movements that I just showed for listening to the contents of table cells, but the output is different. So if the user first presses the key that would tell them if the column contains the search query or not, instead of what is in the contents of the column. So the user can reduce the search space and ignore columns that don't have search results, and they can also navigate to and listen to the specific search results. Okay. So here, for example, it would say 2 occurrences in this column if the user is searching for the word Jill, because the second and fourth row of the table have the word Jill in them. And now, if they want to, they can look at the column, and they can now move down positions in the column, again, in the same way, and actually listen to the contents of Jill. Okay, so how we implemented this, we parse the HTML, and this functions on Wikipedia-style pages. And then we do a tag-based filtering, so we remove tags that we don't support, essentially, and simplify the page. Then we look at the contents of the tag to identify things like tables, the HTML tags. We add the hooks necessary for sprites, and we map the tag content onto keys. And sprites is a modal interface, so you can switch between sprites mode and your regular screenboard keys to control the screen reader. So here's a user study results. We had 2 goals with the user study. One was to compare the performance and usability of sprites to each participant's own accessibility tool. And the second was to explore how interaction techniques impacted participants' understanding of page organization and layout. We wanted to see if it improved the experience for users. And we had 10 participants, 9 were blind and 1 was low vision. And we had 8 tasks, which included things like understanding page layout, revisiting something on the page, working with menus, working with tables, and so on. So the results of the user study were that sprites in general was much better. I'm running low on time, right? Okay, so sprites in general was much, much better at task completion times. So the typical example for tasks that were hard with a screen reader was that 9 or 10 out of 10 sprites users were able to complete the task, and 3 screen reader alone users. And these were on their own machines with their screen readers, and these were, for the most part, expert screen reader users, were able to complete the tasks. So here's an example for a specific task, finding elements within a menu, which was a task that sprites performed well at. And you can see that the timings were the error bars are overlapping in the timing. So there was no time advantage for new Sprites users compared to expert screen reader users. We don't really know how to interpret that, but we're really happy with the task completion rates. So this timing for the screen reader users for the 3 who finished. We're ignoring the 7 who did not finish, for example. And I'm going to, here's looking up the answer to a question in a table. And again, it was 9 out of 10 for Sprites, 3 out of 10 for screen readers. Here, the timings look more different. But again, if you look at the error bars, the overlap is really high. And again, we're only looking at the 3 people who actually completed the task. So I'm going to skip through most of these findings. I will say that for tasks that were really well suited to screen readers, like going through the linear contents on a page, Sprites did not convey an advantage. So it was really great at things that had a really important spatial component, but for finding a piece of, like finding how many headers there were on the page or revisiting something, we didn't see an advantage in Sprites. Its real benefit was in the spatial. And people's comments reflected that, you know, it's easy to remember when you use keys like this. When you have to use a shortcut with 2 or 3 keys, I do use Control sometimes, I use Shift sometimes, but it makes it more complicated. And for many of the things Sprites supports, there are screen reader commands that will do it, but people, even expert screen readers users, didn't always remember them. So Sprites really made it easier to access these features. Similarly with the table, you know, you are counting in your head. It's as if someone took a table out and put it in lines underneath, which is horrible for locating something. But with Sprites, I was able to understand the table. So these are the kinds of benefits that Sprites was giving people. And here's a summary of the sort of the web page tasks that everybody could complete, and then there were 5 or 6 tasks that Sprites was better at. So we definitely saw the screen reader outperforming Sprites in some tasks. The timing information was inconclusive, but we feel that the benefits of Sprites seem to be with its cognitive load and its ease of understanding spatial information. And that is the end of my talk. In future work, we are trying to create a even more robust implementation of Sprites. What you saw today was primarily proof of concept sufficient for a study. We're hoping to deploy it as part of the Web Anywhere screen reader and get it out there and get some longitudinal data on its benefits. I'm happy to take questions now if there's time. Thank you.
Hi, Daniela Napoli, Carleton University. Reflecting back on your user studies, could you talk more about the learnability of Sprites?
Yeah, it did not require a lot of training, but there were definitely aspects of using Sprites. So the question was about learnability of Sprites, and it was sometimes unclear where things were going to be mapped. There was a learning curve to switching back and forth between modes. So there were definitely some challenges that we need to look at in the future.
So I have a question. So how do you think this could be potentially generalized to explore maybe like 3D data, or does, you know, different pages have different layouts that the user, like using this interaction techniques, can transfer between different pages?
Yeah, so I think it's most useful when you're working with a site where there's like a consistent menu structure and you can benefit from learning that layout over time and reusing it, for example. We have not looked at it for 3D interaction. That's a very interesting question. Whether you could use a keyboard in like a virtual or augmented reality kind of setting. We have been looking at whether this benefit would be useful in mobile phone interfaces. So we're thinking about tangible overlays for phone screens to see whether some of the same benefits might apply. And there it's a little bit less clear cut because the swiping through elements covers a lot of ground. It's more like there's additional features like maybe going back and forth between apps or cut and paste that might be well suited for tangible input. So we definitely have been thinking about this across. We've also looked at tangible interactors for desktop interfaces. We've been thinking about where and when do you want to augment screen reading as a starting place for tangible interaction. But the keyboard is, and in the phone case, the sort of phone case that has a little bit of tangibility, have this advantage of deployability that we really like.
Mm-hmm.
Yeah.
Yeah, that's all. Thank Jen.